So everybody has a chi-square GOF test on the calculator? Yeah? Sound good? All right. We're kind of phasing out those old TI 83s and TI 82s. They're kind of old. So good news. Okay, in our textbook, they spend about 5 pages how to calculate the chi-square statistic. Observed minus expected squared divided by expected, but our calculator is going to do the calculation for us. Okay. So when you do a chi-square test, did you click on it? Press enter. When you're on a chi-square GOF test, press enter. And it asks for, where's your data? In list 1, right? We're gonna put data list 1. Our observed values are gonna go in list 1. Our expected values, the O means observed, the E means expected. Our expected values are all gonna go in list 2. And then we just calculate. So really all we need is observed values and expected values. The observed values are always given to us. The expected values, we have to calculate. And you'll see that when we do a problem today. So we're going to do the M&M's experiment. If you had regular M&M's, this would have been very useful. So I'm just going to generate some. We'll do regular M&M's, we'll do peanut M&M's, and then we'll do another example that uses chi-square statistic a little bit differently. There are 2 ways to do this. We can talk about comparing multiple proportions, or we could say all the proportions are equal. In that case, it's called a uniform distribution. So uniform distributions are slightly different than comparing multiple proportions. So we're going to look at regular M&Ms, and I need to look it up real quick. All right, maybe I might figure it out. So our hypothesis for regular M&Ms, we want to know do M&Ms follow the following proportions? Okay, so the company that makes M&Ms, they put so many in a bag. And then you open the bag and you get different colors. Are what you're getting and what they say the same? Well, that's called the claim. Remember the claim thing? Okay, they claim you're supposed to get 12 yellow M&Ms in your bag and 16 blue M&Ms in your bag. Are we getting that? So we're going to test that using a chi-square test. Okay. I went to the Jelly Belly factory in Vacaville, California, or it's near Vacaville. Near that town. I forget, it's just before East Bay, up in the Bay Area. And they had the quality control people, and they were putting Jelly Bellies in a box, and they were making sure that on the side of the box it said 10 ounces of Jelly Bellies, and there's someone weighing. They were weighing like every other one. This is quality control supervisor weighing boxes of Jelly Bellies. That was his job. If there weren't enough Jelly Bellies, put some in. If there were too many, take some out. Okay. So there's people that have this job to make sure you're getting what you're supposed to get. Just like with Snickers candy bars, you're supposed to get a certain weight of Snickers candy bar. If it's too light or too small, you're going to take it out, get rid of it. Okay. So the probability of blue, I believe, is 0.24. 24% are supposed to be blue. Probability of being orange is 0.16. I gotta double check these. I'm going off of memory. Probability of red is 0.13. Probability of brown 0.13. Probability of orange is 0.14. Probability of green is 0.20. And let me double check. I gotta find this to make sure I got the right numbers. I'm sure I'm wrong. They should add up to 100%. 24% blue, 20% orange.
Did you put your O's for orange? or-
20% is orange. Let me go exactly what I follow this thing. 20% orange. 16% green. Did I get that one? No, I put 20 for green. 14 yellow. 16 green. 14 yellow. This must be the yellow. I put an O. I went, oh, yellow. 13 red, 13 brown. Oh, yeah, I got the red and the brown and the blue. All right. So that's what you're supposed to get. Okay, so that's your hypothesis. That's step one. Okay, there's again, there's another way to write the hypothesis for a chi-square test when you have data that's uniformly distributed. We could just write that these are uniformly distributed. So this is our null. The alternative is at least one proportion is different. So if one proportion is different, then we're not getting what the company says we're getting. Okay. All right, we're on the calculations. The calculations is the big part because that's where we're going to construct the observed and the expected values. So I'm going to figure out what we observe and what we expect. So this is the part where if you did in fact bring M&Ms with you, you open up your bag. Don't open up your. We're gonna do the peanut M&Ms in a little bit, but if you got a bag of M&Ms, you separate them by color. Anybody ever do that, or was that only me? I'm the only one that separates them by color. A little bit, a few people. Okay, so you separate them by color. You got. It's funny because they all taste the same anyways. The color doesn't have any flavor like Skittles, but you separate them and you count how many of each color there are. Okay. So this is going to be data. And we got our totals. The observed data, so we had blue. We had 12 blue, orange, and red, and brown, 8, yellow. I need a bigger table or a bigger board. Green. Total. All right. So I opened up my bag of M&Ms and that's what I got. Well, actually, it's not total down here. This is going to be our chi-squared statistic. Okay, so what did we expect? How many blue M&Ms would we expect? Well, we got to figure out the total. I got 54, right? 22, 32, 40, 56. I added up wrong. Unless I just did my math wrong again. 12, 22, 32, 40. 24, 54. Yeah, that's right. So how many would I expect? The expected value is n times p. So n is 54. So I'm going to do some tag work over here. I'm going to find the expected values. And this is all done in a calculation. So I'm going to do blue. 54 times 0.24. Orange. 54 times 0.2. Red. I can do all that in these spaces, but I just want the numbers. Okay. Well, let's just go jump forward. Usually I do all of this by hand, but I'm gonna jump forward. And I'm just gonna do this on the calculator. So our calculator, we need the expected values. So let's go ahead and list one. Let's enter these numbers in list one. Make sure you clear list one. And list two, we're gonna enter our expected values. So list one, you got those numbers in there? In list one, make sure there's not other numbers. So make sure you can go down that there's not more numbers in list one. Okay, list two is where we're gonna enter our expected values. These numbers are the expected values, so let's go ahead and do that. For list one, entry number one, make sure you clear everything in list two. Enter 54 times 0.24.
Would it be 56?
Or, oh geez. 56 is the total. Why did I keep writing 54? Thank you. 56. Good catch. Kind of threw in everything off. Barely. Okay. So you don't have to do this by like side work because we can do it in the list too. Right here in this spot, put 56 times 0.24, press enter, and a number is going to pop up. And what number is that? 13.44. Okay, so do that for each of these, and that's our expected value. So find all the expected values. Anybody get them all? Did you get all those numbers yet? So these numbers here, so I gotta get rid of all these numbers. So yeah, there's zeros there. I'm gonna get rid of these. Oh, that's why I want to clear it first. So that's all the numbers. All right. Okay, here's what the statistic does. Again, I'm comparing these two numbers. What's the difference between those two numbers? What's the difference in blue? I got 12 blue M&Ms. I was supposed to get 13.4 blue M&Ms. I got 10 orange M&Ms. I was supposed to get 11. That makes sense? What's the difference? 10 minus 11. That's the observed minus the expected. I'm going to subtract the two numbers to find the difference. Difference means subtract. So I subtract the two numbers. Then I square the two numbers. Square the two numbers to get my expected value. And then I'm going to divide by the expected value. That gives me this chi-square statistic. So I'm gonna have to do that math for every one of these. To get these chi-square values. I'm just gonna do it one time, we're gonna do the rest on a calculator. Like I said, we don't have to do it all by hand. But if there's a big difference, like red, I got a lot more reds than I was supposed to get. I got a lot more greens than I was supposed to get. I got less yellows. Like there were only 4 yellows. I was supposed to get 7. So all of this combined, instead of again doing a 2-prop Z test 6 different times, I'm just gonna do a chi-square test. It'll compare all of these. Just tell me if there is a difference. If I get a really small p-value, I'm going to reject. That means we got difference. We got something different if we reject. Okay, so that's coming up. We have data in list 1, we have data in list 2. I'm going to calculate this chi-squared value. I'm going to do the formula. 12 minus 13.44 squared divided by 13.44. We get a negative number, but then we square it. A negative number squared is positive. That will give me this value, and I'll have to do that 6 different times. But again, we can do it on our calculator. So let's just do it on a calculator. Stat test chi-square GOF test. Did you find it? The GOF test? Okay, do the GOF test. Default X list is list 1, default Y list is list 2. Calculate.
It's asking for a GF.
Oh, thank you. Degrees of freedom. Degrees of freedom is K minus 1. Okay, usually it's N minus 1, N is 56, but we're not gonna do 56 minus 1. We're gonna do the number of categories. So K is the number of categories. There's 6 categories. So K represents the number of categories. So we have 6 minus 1, which is 5. So DF is 5. Thank you. There's 5 degrees of freedom in this problem. Calculate. Okay, what are we calculating? We are getting a calculation. We're going to get a chi-square statistic and a p-value. Okay, this is where we're going to deviate away from the book again. There's a chi-square table in the book. There's a chi-squared critical value, which when you do problems 7, 9, and 12, they're going to ask for the chi-squared critical value, but we don't really need that. We need the chi-squared statistic, which is the sum of all these numbers. Chi-squared is, what did you get? 4.28. And the p-value?
0.509.
0.509. Okay. Everybody agree? Okay. What's a really small p-value? I mentioned it already. If the p-value is below 0.05, we're going to reject. And say at least one proportion is different. Well, are we going to reject? Okay, we're not rejecting. That's a large p-value. P-value is less than 0.05, we reject. Okay, this is ringing a bell, I hope, for most people here. P-value is greater than 0.05. We're going to fail to reject. So we're on to our conclusion already. We're going to fail to reject. We fail to reject. There's not enough evidence that at least one proportion is different. In other words, I guess that's what they claim. Those are the proportions claimed. That's what we got. We got what the company said we were going to get. These numbers are not different than those numbers. There's no difference. The null hypothesis is like saying there's no difference. The alternative hypothesis is saying there is a difference. So the company put the M&Ms in a bag. Well, the machine does it, obviously. And we got what they said we were going to get. When you're on chi-square GOF test and you're looking at your calculator, there's a bracket underneath at the bottom, and it's called the CNTRB. Did you notice the CNTRB? Those are called the contributions. Each of these chi-squared values are called contributions. They contribute to the chi-square statistic. So we're going to use this to find the contributions. So if I did this math, 12 minus 15.4 is 1.4. 1.4 squared is like 1.9, almost 2. 2 divided by 13, that's like 0.2. Okay, what's the very first contribution you got? 0.15. Use the arrow key, use the right arrow key and go to the next contribution. What's the next contribution? They're all up there.
0.128.
0.128. Next. It gives us way too many decimal places.
1.01.
1.01. Next one, gonna be a really small number.
0.0712.
Okay. And this one might be a little bigger,
1.88.
1.88. That's the biggest contribution. And the last one,
1.03.
okay, and then the sum of all those numbers is actually 4.28. That's the total. That's the chi-square statistic. So if I did this calculation, if I subtract these two, square it and divide by this number, subtract these two, square it and divide by this number, subtract these two, square it and divide by this number, that's where that comes from. Okay, big numbers. If that's a big number, a big contribution, that means there's a big difference. The bigger the number, the bigger the contribution, the bigger the difference. The bigger the number, the bigger that difference. The smaller the number, 0.07, the smaller the difference. Round M&Ms. Pretty close. Pretty close to what we expected. Okay, so small numbers close to 0. Like if the expected value was 10, and I observed 10, and take away 10 is 0. My contribution would be 0. There would be no difference. I observed 10, I got 10. That makes sense? All right. So that's all the calculations. That's the conclusion. That's answering the question for a chi-squared statistic. All right. So that's one. There's two questions where you actually have to, in the chi-square test, problem 7 and problem 9, they gave you the probabilities. So I just want to point you to problem number 7 and problem number 9 real quick, so you can see these two problems. How old are moviegoers? Ages of moviegoers. Page 532. We are given the percent of people that are 2 to 17 years old. 22% of moviegoers are adolescents. 21% of moviegoers are 18 to 24 years old. You guys see all the percentages there? Just like this. They got percentages of moviegoers. Then we sat out at a movie theater and asked people their age and put them into a category. We're counting. This is qualitative data. We're counting how many people are in each category. We have multiple proportions. Okay. There are 5 different proportions. 22, 21, 24, 14, and 19. We got all these percentages. We have the observed values. There were 240 to 17-year-olds, 214, 18, 24-year-olds, 183, 156, 207. Those are called your observed values. These are what we observed. How do you find the expected values? We're going to multiply the total. So it said there were 1,000 people surveyed. That's the total. That's N. N is 1,000. So we're going to do 1,000 times 0.22, 220. So the very first chi-squared statistic that we're going to calculate, we're going to do the observed value, 240. 240, take away 220 squared, 400. divided by 220. 400 divided by 200 is about 2. The very first statistic you're gonna get is about 2. I did about half of problem number 7 for you just now. Or what you can do is take your observed values that are all there, put them in a list 1, which I would highly recommend. The expected values, got to calculate the expected values, put those in the list 2, do a chi-square GOF test. Follow the 3 steps. All right, I want to refer, I mentioned there's a chi-squared critical value. So I just want to mention this. You'll see this table. This is table 6, right after table 5. So if you flip to the back of the book, in the appendix, A16, A17 is standard normal table. A18 is the T distribution. Guess what's on A19? The chi-squared distribution. Okay, so we got another table. We got a table for this information. We got different alpha significance levels. When we did confidence intervals for variation, we skipped 6.4. That was confidence intervals for variation and standard deviation. We could have used this table in 6.4 and 7.5. We skipped those because it wasn't really important. Now we're doing chi-squared. We're going to use the table. I put a big box, a big rectangle around 0.05. Alpha is 0.05. Okay, we're going to use those numbers. Degrees of freedom are on the left. I'm going to go down to number 5 and go over to 0.05. I see chi-squared critical value. This chi-squared statistic, chi-squared critical value is 11.071. Everybody find that number? 11.071. That's called the chi-squared critical value. If this number is bigger than that number, I would reject. This number is much smaller than that number. I fail to reject. 4.28 smaller than that number. Fail to reject. So let me draw a picture of the chi-squared. Like a normal distribution, it's at this the skewed right distribution. 0 is down here. 100 is like way over here. So our chi-square, our cutoff is 11.071. Chi-square critical value is 11.071. So this area over here, this is called the rejection region. This is just extra information. Alpha is 0.05. Okay. So where is 4.28? Here's 0, 4.28, there's 11, so it's about halfway in between. Here's 4.28. Guess what the area to the right of 4.28 is? 0.509. That's the area to the right of 4.28. So if I got a number over here, if I got it like a 12 or 13 or 20, I would reject. Okay, so that's just rejection regions. That's using the table. Problem number 7. Problem number 7. There were 5 age categories. There are 5 age categories. K is 5. There's 5 categories of age groups. That means there's 4 degrees of freedom. So I'm not going to use 11.071. I would use 9.488 for my critical value. But ultimately, this table does not give us a p-value. If I go down to 5 and I start going across, I'm going to look for 4.28. I see 1.61 and 9.23. Alpha is between 0.1 and 0.9. That doesn't really help us. It doesn't actually give us, the table does not give us a p-value like the standard normal table. Another way to do this, another way to find this p-value is using the chi-squared CDF. Did you ever see that one? I never talked about it before. It's on there as well. Press stat. Go to vars. Chi-squared CDF gives us an area. Chi-squared cumulative distribution function. I'm going to put in a lower bound, 4.28. I'm going to put in an upper bound, a big number, like, oh, look, there's 100. And I put in the degrees of freedom. Chi-squared CDF will give us the p-value. So I enter those values. I should get 0.509. I'm sorry,
On the calculator.
second bars. So it's in distributions. Remember the normal distribution, T distribution, T CDF and all that stuff. There's a chi-squared CDF. There's a chi-squared PDF as well, but we don't hardly ever use chi-squared PDF. So I give us the area to the right of 4.28. If I want the area to the right of like finding that alpha 0.05, 11.071, 105, that would give me 0.05. But again, we don't have to do all that. That was kind of extra information for understanding chi-square and chi-square distributions. Are we ready for peanut M&Ms? We brought some peanut M&Ms. I'm pretty sure peanut M&Ms do not follow that probability because they bag them differently. This is actually in the book. It's lost my page. I'll refer to you page number. I believe it's example 3. Try it yourself, example 3, page 531. A researcher claims that the number of different colored candies in a bag of peanut M&Ms is uniformly distributed. So we have to understand this idea. So there's 2 different ways to do this. We could compare multiple proportions, which is a uniform distribution. That just means all the proportions are the same. All the proportions are equal. So I'm going to write it like this. Do peanut, or I'm going to use R. Our peanut M&Ms uniformly distributed. Uniformly distributed, question mark. So for uniform distributions, I could use the same thing. I could use probabilities. I could say probability of blue equals probability of orange, which equals probability of red. I could say they're all equal. Or I could write M&Ms, peanut M&Ms are uniform. Well, if that's the null, what's the alternative? If they are uniform or they are not uniform. Yeah, I'm gonna ask you a couple of people about peanut M&Ms. Now you get to open your peanut M&Ms. This is your dessert. Unless you don't want to eat them. But you need to open them and separate them by color, and we're gonna count how many. We're gonna count how many there are of each color. And we're gonna do the calculations here. We already got a hypothesis. We're on the calculations already. All right, so what did we get? Okay. 7.
Oranges I have 2, 4, 6, 7. That's all.
7.
And then 1, and then 2, and then 3, and then 5.
25. Regular M&Ms got 56. Peanut M&Ms, you get 25 M&Ms in the whole bag. How much did the bag cost? $1.50. So how much is that per M&M? That's like 25 divided by 6. That's like 40 cents for one M&M. Oh, wait, I did that math wrong. I did that way wrong. 1.50 divided by 25. 6 cents. So one M&M, one peanut M&M costs 6 cents. Interesting. They better be good. Okay, you open up your bag of M&Ms. What did you get for your distribution? How many blues?
5,
You got 5. Orange,
7,
7, same. Red,
5,
5.
brown 2,
Brown, 2, got the same.
6 yellows,
6 yellows,
and 2 greens.
2 greens. Can you see that that distribution is different? It's obvious it's not gonna be the same. Well, we're stating the M&Ms are uniformly distributed. So you're gonna take your colors and see if your bag is uniform. We're gonna take your colors, see if your bag is uniform. We're gonna see if your bag is uniform and if your bag is uniform. Does that make sense? So you're gonna have different numbers than what I wrote on the board right there. You have your own numbers. They all have their own numbers. So this is the plan. Usually when I do this, everybody has a bag of regular M&Ms and everybody gets different problem or give it different numbers, different P values. Some people will reject, some will fail to reject, okay? What we want to know, is there uniform distribution or is it not uniform? Okay, so there's the numbers. There's what we observed. Now we got to find the expected values. Okay, this is the hard part. This is what confuses most people in statistics. Okay, the most confusing thing that we do is find the expected value for a uniform distribution. I don't know why. There are 25 M&Ms in the bag. There are 6 colors. How many would you expect to be blue? Here's the math. Expected value is N times P. So N is 25, P is 1/6. 1/6. There are 6 colors. 1/6 of them should be blue. 1/6 should be orange. 1/6 should be yellow. We add all those up, that would make 25. What if there were 5 colors? Then I would divide by 5. If there were 10 items, I would divide by 10. So I'm gonna do 25 divided by 6. That's where I did that math, that 4. I got the 4 earlier. Six times 4 is 24, 4.167. I'll round up. It's a uniform distribution, therefore, all expected values should be the same. For uniform distributions, so again, we have 2 types. We can compare multiple proportions. We are comparing multiple proportions. But notice we're using observed and expected values. We're not using proportions. Now we do the math. What's the difference between all these numbers? I'm going to square them. That's what this formula does. Then I'm going to divide by the expected value. I don't need to do all that. Calculator does it for us. So let's do it. Let's do a chi-square GOF test, but first we have to enter our data into list 1 and list 2. There's list 1 of the observed values, and again, you 3 are going to be entering your own observed values in the list 1. Everybody get 7.87? You guys get that? 7.87? Yeah, okay. 7.87. P value 0.163. CNTRB. One point nine two. 1.92. 1.4. 1.12. 1.32. 0.16. You guys able to find the contributions? These numbers. That's where it came. See that?
How we know one device?
There are 6 colors. And the uniform distribution tells me that I should get the same number every time. So if they're uniformly distributed, I open that bag of M&Ms, I should have the same color of every color. The same number of every color, but they're not the same. They're supposed to be all the same. Like there was one red M&M and there are 2 brown M&Ms. I thought for sure that we were going to reject, but we didn't. Why? P-value. We failed to reject. There's not enough evidence that there is a difference. Anybody get a p-value below 0.05? Gabby, did you get a p-value?
Yeah, but I'm not there yet.
You got a point what? 0.44. Okay, that's still above 0.05. So that's still failed to reject. So looks like we're all failing to reject. I guess they're giving us uniformly distributed M&Ms. What do you think? Yeah. Even though the numbers are a lot different, they're not significantly different. This is a chi-square test of significance. So again, there's 2 problems. Two of the problems you have to do a chi-square test for proportions. The other one you have to do a chi-square test for uniformity. Uniform and not uniform. And to be honest, I think the problem on the final exam is a uniform distribution. I think it's a Skittles question. I could check to make sure, but I'm pretty sure I just checked it last night. I'm pretty sure it's a Skittles. Are Skittles uniformly distributed? Cool. So small p-values mean M&Ms are not uniformly distributed. The company says this, so we don't have enough evidence against the company's claim. I guess they're right. I guess we're getting what they say we're supposed to get. All right. So that's called a one-way table. There's other chi-square distributions, which I'm gonna get to. I'm gonna let you work for about at least get through problem number 7, so about 20 minutes. I'll let you work for 20 minutes, and then I'm going to go over 10.2. I'm just going to talk about 10.2 and give you some direction, even though, excuse me, I didn't assign anything from 10.2. I'm not testing you on anything from 10.2. I just want you to be aware that there's other chi-square distributions. Any questions? You guys are free to eat your M&Ms now or donate them if you want. I'm trying to cut sugar myself. I have been for about 4 weeks now. I don't know if it's working. I just got some cheesecake. It's cheating, cheat day. All right. All right, so doing this chi-square test of association, I'm going to just do an example from 10.2. This set example is kind of spiraled throughout the section 10.2. Gender and favorite way to eat ice cream. Okay, I think it's silly. Like, do you like your ice cream in a cup or in a cone? An ice cream sundae, an ice cream sandwich, or some kind of other ice cream method. Okay, so we're looking at 2 variable data. This is on page 536. So the example on page 536, comparing 2 variable data. If there's 2 variables, we'll get a big old table. Okay, there's a horizontal value, that is your favorite way to eat ice cream. There's a vertical value or vertical variable, that is gender, and we're going to decide what is your favorite way to eat ice cream, and is there an association or is there not association. So when you write your hypothesis, we're going to say the 2 variables are independent or the 2 variables are not independent. We're going to say the 2 variables are associated or they're not associated. So we don't really need really need symbols anymore for a chi-square test of association. So in step 1, we're going to write just our hypothesis. We don't really need to write it in words. We say that the 2 variables, ice cream, I'm just going to call it ice cream style, ice cream is there is an association. Let me make sure that I'm getting this I think I skipped the page here. Let's just do not association. Let's do the first one. Let's do independent ice cream. Style of ice cream is independent or dependent. Yeah, this is the most common methods. Style eating ice cream is dependent of gender. Not independent is the same as saying dependent. You remember back when we did this in chapter 3, we had 2-way tables and we had to test or do a calculation, and we did a multiplication rule for independence and dependence. Okay, we could have just done this test way back when it was really confusing with probability calculations. We could have done a chi-square test of independence. So now we're going to do the calculations. What we need is our chi-square statistic, and we need a p-value. Okay, we can't shove this into a list, this information. We can't just put it into a list So we're gonna put into what's called a matrix. And page 541 kind of shows the calculator matrix. It doesn't show how to get to the matrix. I'm just gonna explain it. You're gonna enter the data into a matrix in order to get the information that we need. So this table is a 2x5 table. There's 2 rows and there's 5 columns. So the matrix, I'm gonna do it right here. The matrix is a 2x5 matrix. There's 2, this means rows, and that means columns. Okay. So I'm just gonna have you do this real quick. Go to your calculator, press second x raised to the -1 power. It's the like the 5th or 6th button down on the left side of your calculator. Is matrix MTRX or MATRX is matrix. And we're going to enter the matrix. That was kind of a joke about the movie thing. We're entering the matrix, okay? New place, new Super Mario World. My kids were playing Super Mario today. Those are pretty cool. Go all the way over to edit. We're going to edit the matrix. And we're going to make a 2x5. So the very at top, it says row and column. You might not have anything in there. It might say 1x1 right now. We're going to change it to a 2 and a 5. 2x5. 2x5. These numbers right here. Then all of a sudden, zeros are going to pop up all through in there. This is like entering data into a list. We're entering data into the matrix. What data are we going to enter? We're going to enter the favorite way to eat ice cream. We're going to enter the numbers that are on page 536. Favorite way to eat ice cream. So in our matrix, we're going to enter these values. So this is how it looks. 592, 300, 204, 24. You just press enter, or you can use the arrow keys to do it. So that's your matrix. Again, page 536. Yeah. That's all we need to do. Okay. Remember previously there was this thing called expected values. The expected values are calculated based on these numbers. The expected values, we're gonna add up all of these, get the totals. We're gonna add up each of the column and get each of the column totals, and then the table total, and do row times column divided by table total. Expected value calculation for 2-way tables is slightly confusing and a lot of math that we don't need to do. So all we need to do is do a chi-square. We're just going to do a chi-square. This is called a chi-square test. Not a GOF test. The GOF test is for one variable data or a list of data. We're just going to do a chi-square test. So go to chi-square test on your calculator. You can quit this screen. You can quit the matrix screen. So press second mode. Let's just quit. And you're going to go stat test. And it's just a straight chi-square test. Press enter. We're going to enter the chi-square test. Observed, matrix A. Expected, matrix B. Calculate. Oh wait, does it ask for degrees of freedom? Does it ask for degrees of freedom? No. We don't even need, degrees of freedom is actually 3. This has 3 degrees of freedom. It's R minus 1 times C minus 1. So R minus 1 is 1, C minus 1 is, 2 minus 1 is 1, 5 minus 1 is 4. So there's 4 degrees of freedom. There's 4 degrees of freedom. Not really important because calculator is just going to calculate chi-square and p-value. Okay, what's our chi-square? eBay.
Or 5.
And p-value?
1.0.
Is there an E?
Oh, -1.
Yeah, when you say 1 point something. No, there's an E on there somewhere. All right. So there's a p-value of 0.0001. Hey, if you didn't learn anything statistics, you learned what scientific notation is, I hope. About the only thing you learned in this class. No, I'm just kidding. Think back of the first day you walked into this classroom. You didn't know anything about statistics, and now you know all this stuff, and you can teach it now. Oh, they're looking for tutors too, by the way. You want to tutor statistics, in the tutorial center. Always looking for. It's really hard to find someone that can tutor this class, right? Like, I mean, just thinking about learning it and then teaching it was a whole other level. All right, so we got p-value. Reject or fail to reject? What do you think? P-value is low. Reject the HO. Okay. We're gonna reject. Where's my? Oh, there's my hypothesis. We're gonna reject. Not that one. Not independent. So what is it? Dependent. Gender and ice cream, favorite way to eat ice cream are dependent. So how you like your ice cream as a cone, as a sundae, or your gender is dependent on those things. Okay. So just looking at the numbers, I want to know what the contributions are. Did they give you the CNTRBs? Did you see that? We did a chi-square test. We didn't get the contributions. Okay, so calculating the contributions, the expected values are given to us. Oh, I can find the expected values. Do me a favor and enter the matrix again. Press second, x raised to the -1 power. Go over to edit. And now go to matrix B. There's stuff in matrix B. There was nothing there before. Now all the stuff in matrix B, guess what those numbers are? Those are called expected values. So if I want to know the contributions, I could find the expected values. What is it? 546, 346, 209. Yeah? Those are all on page 559 down here. So that's how I knew what they were. Okay. So in order to find the contributions, we have to do this formula 8 times because there's 8 different values in there, or I'm sorry, 10. There's 10 different values in here. So in order to find each contribution, which gave the biggest contribution? Well, the numbers that were farthest apart. So if I look at the numbers, 592 males ate their ice cream in a cup. We expected 546. Oh, we're off by about 50. Let's see, are any other numbers that big? The sundae males that eat ice cream sundaes, that was a small difference. Ice cream sandwich, we observed 24, we got 24. We expect 24, so that's no difference. Yeah, it looks like males and females eating their ice cream out of a cup. There was a big difference there. Even though there was a lot from those groups, there was a big difference. So those are probably the biggest contributions. Therefore, that contributed to saying that these results are dependent of each other, dependent on each other. And that is a chi-square test for two-way tables. I just want you to take a peek real quick on page 542 through 545. Just go 542 through 545. They're all two-way tables. Trying to quit smoking, musculoskeletal injury, continuing education, ages and goals, vehicles and crashes, library and internet speed, Borrowing and education. Notice there's two variables for every one of these things, every one of these topics, two variables. We're just comparing the two variables. Are they dependent on each other? Or is there an association? Are they associated? I was gonna write that originally. Are they associated or not associated? It would be answering the same question using the same calculations. Okay. All right. Think we're done here with our statistics world. We've passed Super Mario Statistics World number 8. I think level 8, right? That's the highest world we've got to.